Good morning, everybody. It's my pleasure to introduce my friend Paul Danehy. We went with our wives on a trip to Niigata, Japan, back in 2005, which was a heck of a lot of fun for sister cities. Paul graduated from the University of New Hampshire in '89 with a degree in mechanical engineering and got his PhD and MS in 1995, and I got also mechanical engineering from Stanford. He then spent 5 years in Australia at the Australian National University, which was supposed to have been a lot of fun. And he joined NASA in 2000 and is currently a senior technologist in advanced measurements. He's going to talk to us today about Artemis, and he's going to summarize mission and describe laser and optical measurements that were developed on the flight. So without further ado, Paul, I'm looking forward to this.
Thank you, Jeff. So it's really an honor to be here talking to distinguished alumni here. Damodar, thank you for making the initial connection. I'm sure you guys will agree that it's just an honor and a privilege to work at NASA Langley. And so I'm very happy to reach out, and I hope to be amongst your organization in a few years. So yeah, I'm Paul Danehy I'm in the research directorate, and I'll be talking about optical and laser-based measurements for NASA's Artemis program. And I have a list of my key collaborators, and I guess the point is several of them are NASA civil servants. Some of you may know. Some of them were contractors at NIA, other centers, including NASA Marshall, university researchers, and international folks. So there's a wide variety of people. I'll mention them as we go through the talk. They'll get their recognition. So to give an outline, I'm going to start with an introduction to the Artemis program, which probably you folks know quite a lot about already. Some of you may know a lot more about it than I do, but I'll give a quick overview there. I'll talk about why we would want to use optical and laser-based measurements to make measurements. And then I'm going to kind of go through the sequence of launch, entry, descent, and landing, but in my own way. So I'm going to couch the research that we did in terms of a space mission. So for the launch part of it, I'll be talking, and for the entry, I'll be talking about a technique called laser-induced fluorescence, where we did various measurements for both the launch vehicle and for the Orion entry vehicle, and some fundamental research as well about the landward turbulent transition. And for the descent part, it will be talking about a technique called the femtosecond laser electronic excitation and tagging fleet. And then when we talk about landing, I haven't done a lot of landing work here on Earth, but we're talking about landing on the moon. And for that, we're going to be talking about a planar laser-induced fluorescence technique again, and a technique called photogrammetry, which I'll go into some detail on. So I want to have a disclaimer. My group kind of had some impact on the Artemis program. It was fairly limited, but there are certain measurements that we did that I think were more important than others. Many of the things I'm going to be showing you were just kind of motivated by the space missions, but more on the fundamental research and instrumentation development program. So I just don't want to overstate our contribution to the project. Some things that we've done, we've taken some data that's very relevant, and it maybe hasn't had impact yet, but we hope it will. So quick overview of the Artemis program. We have the Space Launch System, SLS, with the vehicle on top, the Orion. I'm not sure, I guess. Yeah, it's going to be hard to use I'm going to change my display settings here. Hold on for a second. Duplicate slideshow. So I can use the cursor so people online can see, hopefully can see my, cursor. In fact, I'm going to, okay. So so we have the SLS, the core stage, and the solid rocket boosters. There's the Orion and the service module with its launch abort system. It's all stacked on top. Let me also minimize this. And the first flight for Artemis was in November 16th, 2022, which was a flyby of the moon without any crew aboard. The first crewed flight is going to be no earlier than November 2024. And the first lunar landing is no earlier than December 2025, followed by second and third crewed landings, shown as 4 and Artemis 5. The crew for Artemis 2 has been selected, as you probably heard, and the Starship, SpaceX Starship, is supposed to be the vehicle that's going to be used for Artemis 3 and 4, and for Artemis 5, it's Blue Origin has been selected, and that's a 2029 mission. Now, meanwhile, there's on the Commercial Lunar Payload Service, there's a variety of different smaller robotic landers, and I really want to emphasize that that as part of the whole mission, because we have two instrumentation packages that we've delivered. My group contributed to on 2 of those missions. I'll talk about at the very end of the talk. So now I want to try to convince you that using lasers and optics to measure things is a useful activity. So, we basically are trying to use these lasers and optics to measure both flow and wind tunnels or various ground tests, and also in flight for flight vehicles. So what we can do with these techniques, we can get spatially resolved, non-intrusive, temporally resolved, so instantaneous time resolved measurements with quantified accuracy that we can then use for a variety of different purposes. I have 2 quotes from 2 unfortunately deceased but heroes of mine. Walt Lempert from Ohio State. He said, he inspired me with this quote. It's kind of obvious, but he said, it's amazing what you see if you bother to look. And I think about this almost every day, whether it's the water leaking out from under my car and I look and I put the hose back on. I thought of Walt, and instead of calling AAA, or whether it's if you're developing a new instrument to look at some detailed flow phenomena, it is amazing what you see. A second one is a person many of you knew, Dick Whitcomb. I don't have to tell you all the great things that he did, but I've had the fortune to meet him in about 2008 in a workshop in Williamsburg. It was 1 to 2 years before he died. I'm not sure exactly what year it was, but he told me, I explained what I was working on, flow visualization, and he said his 3 biggest innovations came from studying Schlieren images. And so I want to try to provide Schlieren type data, but better. So quantitative, planar spatial resolved data, for example, for the Dick Whitcombs out there who might invent something new. So we're trying to understand flow physics with these measurement techniques. Why does the lift and drag behavior show that certain kink in the curve? What are the flow features, shock waves and expansions? There's an example. Here's a common underexpanded barrel shock flow, from left to right, showing a lot of the classic flow features. This is a laser-induced fluorescence image, but that's a laminar case. And we can study the transition from laminar to turbulent flow with some work that we did with Bob Novak, who many of you guys probably know. We can look for flow separation, flow attachment, and see those sort of phenomena. And this can lead to understanding the flow, but also creation of new vehicles and new vehicle concepts, flow control, and others. We also can use these techniques to understand how the facilities operate. We have to be able to translate the conditions that we see in a facility to flight. So it's very important to understand that. Also to have boundary conditions that can be used as inflow conditions for computational simulations. So we can use this data to benchmark computational codes. So we can measure things like pressure, temperature, density, velocity, hopefully 3 components. And then we can use those to either evaluate CFD models or maybe compare 2 codes, see which one gives the better answer, or to develop new models for the CFD codes. So one of the efforts that's underway at Possible and a couple of our different facilities is to simulate not only the vehicle flying in the wind tunnel, but the wind tunnel itself, because the wind tunnels, as you know, have many artifacts like boundary layers on the walls. We have to take those into account. So there's an effort both at Unitary Plan Wind Tunnel and the Mach 6 supersonic LAL Mach 6 tunnel to characterize the entire flow field of the facility beyond just a few probe measurements. So there's a lot of computational efforts there as well. So there's interest in non-equilibrium. And another big trend that's occurring at NASA these days is instead of the workhorse, time averaged, Reynolds averaged, and average Stokes computational codes, there's been a lot better ability to reproduce experimentally derived flows by using unsteady calculations, things like large eddy simulation, and those are unsteady codes that have time resolved information, and so that's pushing the measurement techniques to go to more time resolved, higher speed information. So what kind of time frames are we talking about? Well, these images you see up top, the flow velocity is probably about 1,000 meters per second because it's a heated jet, it's supersonically expanded. And that the flow scales maybe on say a 1 millimeter, and if they are going 1 millimeter scale going at 1,000 meters per second, it will go in about a microsecond. They will move about a millimeter. So 1 microsecond corresponds to megahertz. So you have to have instrumentation that's on the order of a megahertz to resolve these features and hypersonic flows. So that's what kind of our unsteady target would be, and that's pretty fast for a lot of the techniques. So now I'm going to show you some of the challenges that we're up against. So we've got techniques that work in the lab. We want to try to implement them in a facility. And unfortunately, we have some very hard facilities here at NASA that we test in. So the first one is the National Transonic Facility. Did any of you folks out there work at NTF ever? Nobody? Okay, well, it's definitely a beast of a facility. It's a pressure shell, very large pressure shell with very poor optical access, and then the test section is 8-foot square roughly. And it's for high Reynolds number testing. And of course, they try to crank up the pressure and decrease the temperature to increase the Reynolds number so we can test flight scale vehicles in a small wind tunnel. So that high pressure and low temperatures create problems with frost and high density gas. It's hard to send a laser beam through. There's really very little or no optical access. There's very limited optical access. You see a few windows here, but the actual pressure shell has no windows. We had to put windows in. It's very expensive to run. There's no natural, we can't put water or other particle seeds in to make velocity measurements. So it's a very hard facility to test in. So another example of a hard facility to test in is these measurements we've done in Buffalo at the Kubrick facility. That's a wonderful facility. They have all these pulsed shock facilities, very large scale tests that they can do there, but it's a remote location. You can't be in the measurement area when the measurements are occurring, so everything has to be remote controlled. One of the worst things is the facility only runs for about 50 milliseconds, and our laser is running at 100 milliseconds per pulse, so we get one image per tunnel run, and they only let us run one, maybe 2 times a day. So we're going to get one image per day typically. So it's very painfully slow. Tunnels moving, it's a real pain to test there. And the third case is last summer we took our laser systems down to NASA Marshall, and we had our lasers set up in this room next to a vacuum chamber. The vacuum chamber is where our laser went in, and our cameras were in these little camera enclosures you see here. And again, everything had to be remote controlled, obviously, because it's at low pressure. We have a little flow impinging on a flat plate there. I'll explain that in more detail later. We had to deal with weather, humidity, remote operation, et cetera. Remote, we had to bring our equipment there. So again, very, very different, challenging environment. So our strategy was to develop these mobile laser systems where we could kind of bring everything in there, get it set up as quickly as possible. In some cases, we could get it set up in a week or two. But other cases, it's longer. We want to try to automate everything as well as possible, have reliable computers and so on. And you want to try to have simple methods if you can come up with a simple method to keep the physics simple. And we have 4 of these carts, 2 to doing laser-induced fluorescence. One was for cars, and 1 is for fleet. All right, so now I'm going to take you through the sequence of launch, entry, descent, and landing as seen by our measurements team. So the real launch occurred November 2022. So it was a big success down at Kennedy. So the contribution that we had was we did a base heating study in collaboration with NASA Marshall, and we did this test at the Kubrick facility. Manish Mehta at NASA Marshall was our kind of the PI for the project, and these other researchers at Langley helped with me. So basically, we were doing high hydroxyl radical PLIF visualization and temperature measurements for this SLS base flow. So the challenge was to look at this base flow region on the vehicle where they were concerned with the heating pattern. So the technique we used was a planar laser-induced fluorescence technique. So for that, we take a tunable laser beam. It comes out of the laser and passes through some optics that form that collimated beam into a sheet. That passes into a flow where it excites a molecule that's present. In this case, we're probing nitric oxide, and the nitric oxide absorbs the light in our laser sheet, and it fluoresces at a different color, and our camera takes a picture. And basically, it's at first order, it's just flow visualization, but you can get quantitative. If you do it cleverly, you can get quantitative information. So we can either do nitric oxide, or if we have a flame, we can use that OH, the hydroxyl radical. So that's what we did at Kubrick in this particular instance. So the challenge here was that at high altitudes, the flow coming out of these rocket engines was predicted to come back and impinge on the base of the SLS. And if it did that, it would have increased heating on the base. And in the Apollo program, they had the Saturn rocket had a fifth engine right there at that spot where this heating is going to occur. For whatever reason, they chose to put 4 engines. So there's this flow pattern that comes out, and the computational fluid dynamics simulations were showing that a normal shock sets up here, creating a very high temperature region here and increasing the heating here. So the CFD is showing this, but they were doing experimental measurements. They did a Schlieren measurement. They didn't see any shock wave because the density is very low. And in infrared images, it's shown here, you can see the jets, you see the jet interaction, but you don't see any apparent shock wave or anything there. So there was disagreement between the various people on the project where this was a real effect, if maybe it was just an artifact in the CFD. So they asked us to come and do a test there, and we did laser-induced fluorescence of OH, and we showed that it right where they predicted, the CFD predicted, that's right where we saw a big increase in our signal, indicating a shock wave and a higher temperature as predicted by the CFD. So that flow visualization itself gave them confidence that the CFD was doing a good job, but we thought we could do better than that. And what we did was we tuned our laser to 3 different wavelengths, and we're able to get measurements at 3 different colors, and that's probing different states of the OH molecule, like a low rotational quantum number and a high rotational quantum number. And those high ones are only excited at high temperature. So by graphing them on a single graph like this, if it's cold, this dashed line that best fit would be a very steep line. And if it's hot, there's like lots of population in different states, and it'll be a flat line. So the one over that slope tells you the temperature. So by fitting everywhere in this image, that data, we can get a temperature map as shown here. And the data was ITAR, so I stripped off the actual numbers. But this gave them a quantitative temperature map that they could then use to calculate what the heat transfer would be to the surface. And they had heat transfer data measured as well. But they felt like this fluid flow measurement was a significant contribution. They previously put thermocouples out into the flow, and they did that during the Apollo program as well. And that had like 50 to 80% uncertainty, and our measurement was 10 to 30% uncertainty. So it was a significant improvement in their uncertainty. So they used this information, although they added many more layers of insulation, I think, after this because of various other tests that they did. But they did take this into account when they were designing the thermal protection system on the base of the SLS. All right, so that was our contribution to the launch. So then, of course, the mission took some beautiful imagery of the backside of the moon as it flew by the moon, and then we have an artist rendering of entry. So that's another area where we could do measurements for the reaction control system jets, and also studying transition from laminar to turbulent flow. So let's talk first about the measurements were done at that Kubrick facility, that pulse facility, 1 image per day. This kind of shows the setup. This is the model in the facility. We have a couple cameras looking through these windows, a laser sheet coming down perpendicular to the model. And we'll see that same sort of arrangement from a different view here in this next. So here we're in this Mach 8 flow. There would be a shock wave on the front of this vehicle, but we can't see the shock wave because we're seeding nitric oxide into the flow, and we're exciting that with our laser. So there's no nitric oxide in the oncoming flow. So what we can see here is a separated flow region because we're entraining the NO from a little tube back here. So at low Reynolds number, we see it's a nice laminar shear layer here indicating laminar flow. But then if we do the same thing, the only thing we change is increase the Reynolds number. We then see a turbulent shear layer, and that was helpful for them to figure out where to transition their computations between a laminar and a turbulent case. So that's just looking at the shear layer. We could also look at the reaction control system jets. So here's a roll jet shown, and what we see, if there was no flow, you would see a big underexpanded jet plume like I showed on an earlier chart to be a symmetric plume coming up. Instead, with the flow, the flow coming over the top of the vehicle interacts with that plume and giving this the shape as shown here. So we did that, and then they also had done Schlieren imaging for the same configuration, and the Schlieren imaging didn't even show jets. This laser-induced fluorescence technique is very sensitive. It works great at low pressures where other techniques don't. So by taking these sort of images and superimposing them, here's one image and another image shown in this plane. By superimposing it on a surface measurement of the heating, we can look for correlations or lack of correlations between. And because one of the concerns from the Orion project was that this plumes might be coming out and impinging back on the vehicle, creating the heating pattern. But what this measurement showed is that it was probably just like a vortex roll up around this jet that was causing the heating pattern that's shown in the green, because our jets leave the surface and they don't come back and impinge on the surface. So that was, again, it was very painful. That was in Buffalo, and we could get one image per day. Well, here at the Mach 10 tunnel at Langley, we can do like a 1-minute run. And that allows us to do things like change the angle of attack of the model or scan our laser sheet during the run. So that's what we did. We took advantage of that. We took instantaneous images at 10 hertz. And this is a very similar situation here, slightly different conditions. But again, it's a roll jet, and we're imaging that plume. And then what we could do is we scan the laser sheet as we take the measurements as kind of quasi-steady flow there. And that allows us to develop reprocess that in slices and get like a volumetric measurement. So that was roll jets, and those are pitch jets. And we also had yaw jets as well that we looked at. But we can create these 3D visualizations that show the shape of the structure, and you can see it's kind of complicated how those jets interact with each other and with the oncoming flow. Now that data was compared with computations, and they agreed surprisingly well, again giving confidence to the Orion program that their CFD was doing a good job. So here's a study that we did back about over 10 years ago that was just kind of motivated by the space program. And this comes from the fact that the crew module, even going back to Apollo, would be attached to the service module with these tension ties, and there are these compression pads which are made of a different material than the acreage thermal protection. And so these could either be cavities or protrusions, and then of course the tension ties could stick off the material. And a previous study had showed that there could be up to 3 times higher heating downstream of those during these entries. So we wanted to visualize the flow downstream of these cylindrical artifacts and also try to do velocimetry. So we did this on a flat plate, this wedge model, and we seeded nitric oxide in from a 11 millimeter wide slot. And if there's no trip present, we would just see that smooth laminar flow pass along this plate. But if we have a trip present, in this case a cylindrical trip, it forces the flow to transition to turbulence. And so we looked at that with a couple different ways. So this is an image where the laser sheet's perpendicular to the surface and the camera's looking from the side. And in that case, we can see a laminar flow coming into the trip. And even right after the trip, it's laminar, but that transitions to a turbulent flow further downstream. We varied all the parameters, the Reynolds number, and the angle of attack, and so on to study this. But one of the reasons I wanted to show this is one of the things that was very cutting edge at the time, and is still not widely used, was we developed a megahertz. I should say not we, but Ohio State developed a megahertz rate imaging system that they brought to Langley, and we tested it in this time frame. And you can see these. You can see like the individual same little flow structure tracking downstream about 1,000 meters per second. It's going like a millimeter per frame. So we're able to resolve those little flow structures and see how they proceed. And we can this next round here is these are at 500 kilohertz. They go a little further. But my main point I want to make is that that went through the SBIR program. We were able to develop what was a university demonstration into a commercial product. I think NASA's probably funded, I don't know, 3 or 4 SBIRs. The Air Force probably did 5 or 6 SBIRs. And now we have the laser in our lab. We just received it this year that can allow us to do the same sorts of measurements. So we're very excited to try to implement that here at Langley going forward. So next thing that was inspired by these sort of peat shield measurements was to develop a velocity measurement technique. So in this case, we're going to take that same laser sheet, but instead of having it come out and just make a sheet, we passed it through a special optic, which was a series of cylindrical lenses stacked together. And it creates, instead of a sheet, it created a whole bunch of little lines in the flow. So each little line is sticking off that flat plate. And we take an image, and then we wait 500 nanoseconds and take another image. So this is the initial image and then a delayed image. And you can see the gas moves downstream. And we can use the time of flight, just, change in distance over change in time to get the velocity there. So we use this. This was Brett Bathel's dissertation work. And when we had no trip present, we got the expected, Blasius-like boundary layers just continuously down the whole flat plate. But when we have a trip present, we see the flow separating, and if you zoom in on one, you see the flow is actually reverse flow. This would be zero velocity, and you see that there's reverse flow both behind the trip and in front of the trip, indicating a vortex roll up in front of that trip. So this data was simulated by various researchers, as shown here, and there were no surprises. Their models worked pretty well, but not many people have done this sort of simulations in these flow fields. All right, so we did launch, entry. Now talk about the descent phase briefly. We descend through transonic flow, and there was a test that Greg Brockman ran at National Transonic Facility, and we were asked to do some velocity measurements there. So using the FLEET technique. The FLEET technique, femtosecond laser electronic excitation and tagging, is a technique developed at Princeton. And remember I said I wanted simple techniques because this is the hardest facility I've ever worked in. I wanted to have it to be the simplest technique. So the simplest technique that I've ever used was FLEET. It just takes a single lens. Basically take this femtosecond laser. So that's a really short, like a 10 to the minus 15. It's 100 times 10 to the minus 15. So it's 10 to the minus 13 seconds long, extremely short pulse. And you just focus it down with a single lens, and it kind of does a very gentle laser-induced breakdown of the air, where it just dissociates nitrogen, and when it recombines, it expands to excited state that then fluoresces over some time. So you basically can fire your laser, start taking pictures really fast, and the gas, when it moves around, you can see where it moves to. Okay, so you can either do it at a point or with a line measurement. So this is an example image. So you fire the laser, and then as it moves downstream, you just take pictures of it. And so at a rate of 200 kilohertz, we're acquiring. So that's every 5 microseconds we image where that gas is. And again, you can just measure the velocity of the gas that way. We fit centroids and so on to calculate the velocity. This is, again, the simplest technique, single laser. It's a pretty robust laser. This laser is designed to cut metal on factory floors 24 hours a day, 800 nanometers, so it's kind of near the visible. It runs at really high rates. The fluorescence is in the visible, so you don't need fancy windows. You don't need to put any special gas in because it works in nitrogen. So in theory, it's a very easy technique to do, but in practice, doing it in NTF, not so easy. Here's some of the not so easy. Just getting the laser beam in there, we had to put a pipe that we pull a vacuum in the pipe, and it has to be heated and insulated, and all these remote control windows to direct it because it still heats up and cools, and the pipe bends, and just keeping everything in focus is a real challenge. The laser's well outside of the facility, and it has all these mirrors in there that all have to be remote controlled. The camera has to be heated and cooled. It's very difficult to make these measurements. But we were able to succeed for this Orion test, and our approach here, remember I said that the laser is designed to cut metal. So if you focus that laser beam right onto the model, you damage the model, unfortunately. So we had to roll the model 90 degrees and send the light to the side of the model. So that's what's shown here. We could either look on this side or roll the model and look on the other side. But basically, we sweep the laser beam out away from the vehicle, and then we would sweep. So we'd sweep it away from the model and then downstream and sweep it back. So we would get two planar measurements, time average, planar measurements of two different locations downstream. So this just shows those two measurement planes. And we chose our locations to be where that shear layer is, because that shear layer was expected to change based on the Reynolds number, Mach number, and so on. So this shows an example. Sorry, this is a very busy chart, but we were able to vary the Mach number, 0.3, 0.5, 0.7, vary the Reynolds number, this row versus the next row, and there's different upstream and downstream measurements, which are all graphed here. But the upshot is we produced a data set that can be used for computations, and this was just published this year. So I don't think anybody's actually simulated this yet, but I think it's a data, and you'll see that these axes do have numbers on them. So we're able to get export control to agree to release this data, which was going to be helpful, so the open community can look at that. All right, so we're coming in the home stretch. We're on to landing now. But we're going to land on the moon instead of on Earth. So the problem with landing on the moon or at Mars is we have this plume surface interaction problem. And this has been studied extensively in the Apollo and the Viking programs, but we're taking another whack at it with our current new computational and experimental capabilities. So what can happen, the plume comes down, interacts with debris, and if you have an asset nearby, it can hit the asset. The regolith can be accelerated to supersonic or hypersonic velocities and damage your nearby installations or astronauts or whatever you have there. It also can come back and damage the bottom of the lander, or it can dig a hole the lander ends up landing in, which is not good. So we are studying this phenomena, and there's all kinds of problems this could cause. So you see various examples of this. Here's the Mars 2020 mission landing and it causing all this debris that makes it difficult to land in. So we are doing both our part is experimental. So the first part I'm going to talk about is the plume surface interaction test we did in that big ugly facility at NASA Marshall, that vacuum chamber. We did laser-induced fluorescence, again using the nitric oxide planar laser-induced fluorescence technique. And we were trying to visualize these plumes, figure out where the shock waves are, figure out where they hit the surface. So we had our Mach 5 jet that we seeded with a little bit of nitric oxide, and that was held at a fixed distance above the ground, and it was impinging on a plate. The plate is right along the bottom of this image. And at the very end of this, the jet shuts off. But you can see the gas coming down and then the gas going off to the side. There's no regolith in this case, but there was a series of tests done with regolith as well. This is an example of the same conditions, but just at a higher altitude. And what you notice from this image, there's a barrel shock on the outside here, and the shock wave here, there's like a one shape here, like a triangle shock. This is more of a curved shock. So very different flow phenomena depending on your altitude. And at the very beginning of this run, when the pressure in the facility is the lowest, you don't even see this barrel shock out here. I'll let that cycle through one more time. That's with the shut off there. So at the very beginning, you notice there's just no shock wave out there. As the pressure in the vacuum chamber comes up, you start to see the shock. So these were, we tested at many different altitudes. We also tested at different ambient pressure because higher ambient pressures simulate a Mars landing. And you see for a Mars landing, it's much more turbulent and it's more of a collimated jet because the pressure's higher on Mars than it is in the moon. And this collimated jet's going to drill a deeper hole in the ground than it would on the moon. So that data, there's various computational teams that are looking at simulating that. And then that brings us to the last thing, which is also focused on the plume surface interaction problem. What we're doing is we're trying to use a flight camera system to use like stereoscopic vision from cameras to measure the depth of those craters that are going to be generated on the moon. So we have two different missions, call it Scalps 1.0, 1.1. So 1.0 is flying on Intuitive Machines Nova C lander. We've already designed, tested, and with a lot of people in the engineering directorate delivered these two photogrammetry systems to these two companies. The second one is the Firefly Aerospace Blue Ghost lander. The Nova C system is a 4-camera system. This other one is a 6-camera system. I won't go into many more of the details, but I just want to tell you briefly that how we did the testing of these. And I had my summer students build a crater, a simulated crater for us to use as a test bed. This is paper mache and rocks and concrete mix just poured on top on wet paint. And it looks, I've never been to the moon, but I think it looks pretty realistic. So we have this mounted on a fixture in our lab, and we have an independently calibrated measurement system called V-stars, and that will measure the shape of our crater on any given day very precisely. So this is the kind of the known shape of the crater, and then we can take our measurement system and measure the shape of the crater with our scalp system. It only needs 2 cameras. This other system, you take like 100 pictures, so it's like having 100 cameras, very accurate measurements. But with our system, we just have 2 cameras, and we can then evaluate how well our technique works, and we evaluate the different lighting conditions and so on. The last thing I want to say about the scalp system is because I love lasers. I didn't want to just send cameras to the moon. So the next mission, what we're talking about doing is actually putting projected laser dots onto the surface, and they're going to basically shoot out from take one laser, it's going to split it up into an array of like 20 by 20 laser beams, and that will come and we've got a simulation of this in our lab. We're shooting it off that mirror that's down there, and this is a very noisy image, but what you can see from this, these are side views here and top views, and we're going to look at this top view data, and this is what we would see if we're shooting the lasers down as we land. We'll see the plume come up, and we can measure the top edge of the plume. So over here, we're seeing the edge of the plume come up as we turn this jet on. We sort of blast this jet, and we see the edge of that ejecta sheet come up. So that computational people are excited about having us do that. And so you can see that in the case, there's like this little dot here is going to move from left to right across the image, and that's going to be the data that we'll use to quantify this. So to conclude, I took you through, I guess, my version of launch, entry, descent, and landing, showed some contributions that we've hopefully made to the Artemis program. We're trying to, in some cases, give confidence in the measurement techniques, other times maybe explain why things are happening or how they're happening. We're hoping this data will provide code validation, also just understanding, and we're excited about these flight measurements we're going to be able to do. We're not just working with the lunar missions, but we have the Mars sample return. We're working on a photogrammetry system for them. So I talked about 3 different measurement techniques: the PLIF technique, the fleet technique, and then photogrammetry. And I'll just mention that I could have put a similar presentation for Mars applications together, but and I'm working on some aeronautics work as well and some scramjet work as well. So I appreciate everybody's time, and thanks for your attention. Amadar.
I was going to ask you a quick question. So I believe some of these techniques are developed far along so that you can use it relatively routinely in test facilities these days, right?
Some of the techniques Well, I would say that the ones I have developed have not been able to just be handed over for the most part. We do have one example of we did planar laser induced fluorescence at the Artemis scramjet test facility, and after the initial test, a couple of tests, we ended up handing that over to Rick Gaffney's branch, hypersonic air breathing propulsion branch, and their researchers did the measurements. But I would say in general, we have not been that successful in just handing techniques to. They're just too complicated. Too many things can go wrong. They're even the simplest technique, the fleet technique, the application of it NTF is so complicated. They help a lot. The facility technicians, for example, they keep the camera cool and warm enough, pressure stabilized. They're great, but it's a lot of work. These techniques are not. There are some that are like Brett Bathel's team. They built a new focusing Schlieren technique, and that is simple enough. I think would have potential to be handed over, but stuff I'm doing is not really.
Yeah, actually, my question is, there are a lot of other commercial entities that are developing this kind of systems. So are they taking advantage of these advanced methodologies, so that they can detect the phenomena of the kind that you were citing?
You're asking like outside of
like
NASA?
SpaceX and people like that, so are they calling you up and asking you to instrument their systems during their test processes and see, what exactly is happening with them?
I think the role that I'm gonna answer a different question than you asked, but my understanding of how things are going, say with SpaceX, is they plan to do something, but there are people at NASA who they lean on to give them advice, and they will draw on their knowledge base to an understanding of maybe more scientific or fundamental understanding of some of these things, and kind of give SpaceX advice on maybe a route that they might want to go instead. So these techniques, I mean, I can't think of an example where we've done a test with SpaceX in the wind tunnel for our techniques. I think that if you had asked Kelly Murphy the same question, she might have a lot of examples of doing, phosphor thermography or some other advanced technique to help them. But yeah, I'm not. I know the Blue Origin, we're going to be working with them with the Scalps mission. There's a follow-on Scalps mission. They're doing Eclipse scale lander, a robotic lander, supposed to fly in like a year. We're developing a Scalps instrument for that. So we're going to be working with Blue Origin. For HLS, we offered to help for the SpaceX. They were going to do a demo mission, and we offered to help build a photogrammetry system, and they basically were happy to take our advice, but did not have us. We're not developing a mission for that. I think they're trying to do something similar. So we've published a lot of papers. They're taking our papers and they were putting their own cameras, and they may do some. They've got very clever people working there, so they may be able to redo and we will help them as much as they want. We want them to be successful, and so any way we can help. So we've had a few telecons with them, but it has not been. We're not part of the the HLS SpaceX landings.
Thank you, Paul.
Yeah.
Probably Carpel. You're using lasers for visualization, but NASA's doing a lot of work on using lasers for communication. Have you been involved in any of that?
One of my colleagues who did a PhD here at Langley ended up going to NASA Glenn, and she works in that area. I don't know much about it, frankly, but we have some path there if you wanted further information or something.
I worked on the lunar laser communication demonstration where we actually communicated by means of laser from the moon back to the Earth and from Mars back to the Earth. It's real interesting. I was just wondering if you've been involved in it.
I haven't been involved other than that one connection with a colleague at NASA Glenn.
Has some real advantages in communication.
I totally understand that. Yeah.
Thank you so much. My question is very broad. How do you see China in this whole picture of the vision of the moon, and also specific to the technologies you're talking about? They seem to have big goals. Everybody knows they already have a robot. Now, I don't remember the date exactly they set out to send people there, So two-part question. How do you see China's vision and how do you see their overall plan? And then specific to your technologies, are they where we are? Are they ahead from what you know?
So I would say we're keeping our finger on the pulse there a little bit in terms of their instrumentation development. I just read a very influential paper from China that has given me some insight into some of the things that we're doing. But yeah, I'm not very knowledgeable about it, frankly. I mean, we've really appreciated the imagery. They had the Chang'e landers that had very interesting imagery that we've studied and kind of tried to learn from. But I'd say it's our knowledge and use of anything that they've been doing is very limited. Probably not so the other way around. But yeah, we try to learn from, but I would say that we're discouraged from communicating directly with, if we receive an email from China, we're not really supposed to reply. So we kind of don't make active connections like we might with the German Aerospace Center or somebody like that. So I'd say it's very, very limited, and I really can't comment on the Chinese space program. I don't know much about it, frankly. No, sorry.
Do we have any remote questions?
Good question.
No, we haven't received any remote questions yet.
Well, they are probably unfamiliar with using the chat, if the chat's even working. So,
It's working.
okay, great. Well, I have a question
Sure.
then. This caught my ear. You said you delivered instrumentation to two companies.
Mhm.
So, so did NASA contract with the companies and then they came to you for the
Yeah,
instrumentation?
so the CLPS program, Commercial Lunar Payload Service, the companies proposed to NASA that NASA put out a solicitation to fly missions to the moon, robotic missions to the moon, and to take NASA payloads.
Right.
And they listed a dozen or so payloads, and we were one of the payloads listed.
Okay.
And the different companies could propose to take any of those payloads that would suit them. And so we were actually selected by three out of the first three missions but one of them, they decided that one of them had said they would take every payload. So they wanted to, I think they didn't want to have us deliver three payloads simultaneously all at the same time. So they reduced us to two of the three, and then that's the two that were. So Astrobotics was the third one that they did not, that initially chose us. But so we are giving that, the NASA is paying these companies to take our payload and send it there.
Ah,
And there's
okay.
other Langley developed payloads
Okay.
as well, and they're from the whole agency.
Yeah, well, the reason I ask is that one of the challenge we faced and what they wanted us to achieve is transfer of technology to industry. And when I heard that a company came to you for instrumentation, that would be a big deal. But if you're paying them to come,
We're paying them to come to us and deliver them. Yeah.
That's cheating.
It is kind of cheating. I see what you're saying, but I think that if we want to have these sort of capabilities for future, missions, we need to pay somebody to take them there for us. So yeah.
Any other questions?
This is-
Go ahead, Rick.
This is Rick. We still don't have any remote questions, but we did have a comment from Rich Ancliffe. He says, Paul, you have done a nice job taking these laboratory techniques and applying them in practical applications. Kudos.
Thank you, Rich. Appreciate that.
No, I think it's wonderful. But anyway,
All right. Well, thank you very much.
thank you.
I'll enjoy my coffee. That's very nice mug. I don't know if people online can see that. That's very nice. Thank you.